I want to try one more thing with the DC offset correction before I move on. So in this video I'm going to talk about what I want to do to this DC offset correction. And then in the next video I'm going to actually do it and see how it works. I want to spend some time explaining the math behind this DC offset correction loop, just in case some people are unfamiliar with it. But the schematic might not be the best visual aid for that. The schematic shows you how it's built, but it doesn't really give you a good visual idea of what's actually happening to the signal. So instead I'm going to be drawing up some block diagrams. And just in case you're not familiar with block diagrams, I'll explain the symbols that I'm using to make them. So in my block diagrams I have lines that show where the signals go and little shapes for pieces of the circuit that act on the signal. For a circle with a plus in it, its output is going to be the sum of all of its inputs. And when I put a little bubble on one of the inputs, that means it's inverted. So in this case, B gets added with a negative sign. So here the output is going to be A minus B. If I put a little bubble on the output, that means that the output is inverted, which means that the entire output of this block will be negative A minus B. And I can put these bubbles on the other types of blocks too. These triangles are amplifiers, and I labeled them with their gain. So in this one has a gain of A. So if signal C goes in, what comes out is C times A. For anything else, I'll just draw a little square and write whatever it is on the inside of it. So here's an example of a block diagram that we're going to be seeing a lot of. It's an amplifier with negative feedback. So what's happening here is we have an input signal that's getting fed to an amplifier, which gives us an output signal, but then some of the output signal is then subtracted from the input. And this is the basic structure of the DC offset correction in the ECG circuit. And this formula down here is just a mathematical description of what's happening. So we have some output signal which is equal to the output of this amplifier, which is A times whatever's at the input. So here we have A times some stuff. So what's showing up at the input is M in minus something else. We have M in minus something else. And the stuff that's being subtracted off is B times whatever is currently at the output. So we have B times the output. And what will be interesting to know is the gain of this entire system as a whole. In other words, what's the ratio of the output to the input? So you can do some math to this equation, and you end up with a gain of A, which is the amplifier gain, divided by 1 plus the amplifier gain times the gain of whatever is in the feedback path. So if you replaced this entire system with a single amplifier that had a gain of that, it would do exactly the same thing mathematically. So when I talk about the DC offset correction loop, this formula is going to come up a lot. I don't want to spend too much time on background, but if you're not familiar with block diagrams, then you're probably not familiar with frequency response either. The frequency response of a block just tells you how the gain is different depending on how fast the input signal is changing. The only block I'll be working with in this circuit that has an interesting frequency response is the integrator, which just adds up its input over time. And the gain of the integrator is 1 over j omega RC. So the R and the C are the resistor and the capacitor in the circuit, and the omega, which is this W-looking guy, represents the frequency of the signal at the input in radians per second. Normally when you think of a frequency, you think of it in hertz, which is in cycles per second, but radians per second is the same thing, it's just off by a couple of pi's. I'll be using radians per second instead of hertz, just so I don't have to worry about throwing pi's around. And the J, you can just kind of pretend the J is not there, it's imaginary. So frequency here is on the x-axis, with low frequencies or slowly changing signals on the left, and then quickly changing signals or high frequencies on the right. So you can see that for a low frequency it has a high gain, and for high frequencies it has a very low gain. And to give you an idea of what this looks like, if we have a slowly changing signal at the input of a frequency of omega low, you can see it has a high gain, which means the signal comes out larger at the output. And for a high frequency signal, which changes really quickly, we can see it has a very low gain, so it actually comes out smaller at the output. And one last bit of background before I get into the actual circuit is what the frequency response looks like when you use the integrator in the negative feedback. This is the general form that the DC offset tracking has in the ECG circuit. So from a bit ago we have this expression here for the gain of an amplifier that has negative feedback. So in this case our amplifier gain A is going to be 1, and the gain of the block in the feedback path, which is the integrator, is 1 over j omega RC. And when we plug those back in, we get a total gain for this entire system of 1 over all of 1 plus 1 over j omega RC. This expression that we got for the gain of the entire system is a bit more complicated than the 1 over j omega RC. So if we want to actually plot the frequency response to see what's going on, we're going to have to do one of our favorite things to do as engineers, which is approximate. On one hand, it would be nice to get rid of this 1 on the bottom, because then that would turn into 1 over j omega rc, which is just j omega rc, which is easy to plot. Also, on the other hand, if we got rid of this 1 over j omega rc on the bottom, then it just turns into 1, which is also pretty easy to plot. So if we think about what happens if the frequency is low, which means omega is small, we have 1 over a very small number. And 1 over a very small number ends up being a very big number. And a really big number plus 1 is really not all that much bigger than it was before. So we can say that when the frequency is small, then this term, the 1 over j omega rc, is the dominant term, and we can just ignore this 1. And when the frequency is really high, this term turns into 1 over a really big number, and 1 over a really big number is a really small number. So if the frequency gets high enough, and this number gets much smaller than 1, we can just ignore it and pretend it's not there because it doesn't have much impact on the overall result, so then it just becomes 1. So here I have both of those plotted against the frequency, omega. So when I plot this term, we can just pretend that the j doesn't exist because it's imaginary. We get a line with a slope of rc. And then of course the 1 is just a flat line with a height of 1. And we know that the actual frequency response will follow this line, omega rc, as long as omega is small, which means down here, and it follows this line when omega is large, over here. So it should be pretty obvious of just the general shape of the frequency response, and it'll look something like this. And from looking at this, you can see how it corrects for the DC offset. So for really slowly changing signals, and signals that don't change at all like DC, we can see that we have a really low gain, so those don't get passed to the output. But for a heartbeat signal which changes a bit more quickly, we have a gain of about 1, so that does get passed to the output. And by changing RC, we can change the slope of this line here, which changes how steep this part of the curve is, which changes how quickly it will track out that DC offset. Alright, now on to my complaint with Jason Nguyen circuit. Up here I have an integrator that you would normally make out of an op-amp. When you do some math, you find that the output is proportional to the input voltage added up over time. But you can see from this negative sign that it's also inverting. And down here is Jason Nguyen's integrator. And it looks like he was trying to build a non-inverting integrator. And it sort of worked. So the output does have a term that's proportional to the input voltage added up over time, but also has another term which just puts the input voltage at the output. So in other words, the output voltage is the input voltage plus the integral of the input voltage instead of just the integral of the input voltage. To make that a bit more clear, here's some block diagrams. So here we have the ordinary inverting integrator. And over here is effectively what Jason Nguyen's integrator does. It has an amplifier with a gain of 1 in parallel with a non-inverting integrator. And here's a block diagram of Jason Nguyen's circuit. And down here's the schematic. I left the front end off the schematic because it's not too important here. I also color-coded the components in the schematic so you can see which parts of the block diagram they make up. I've also color-coded the signal lines in the schematic here with red and blue. If you remember, we have differential inputs, so one signal gets subtracted from the other. The signal with a positive sign gets a red line, and the signal with the negative sign gets a blue line. That's also useful to keep track of which blocks in the block diagram invert the signal. And here's the equation for the gain of the entire circuit. It's got 3 parts to it, the front end, the back end, and in the middle here is the gain of the DC offset correction loop. And here I've plotted the frequency response of just the DC offset correction part of the circuit. So the job of the integrator is to look at the output of the circuit and find the DC offset, then feed it back to the input where it gets subtracted off. But Jason's circuit is not just an integrator, it also passes the original signal through, which means that at the input, the original signal gets subtracted from itself, and this lowers the gain. So if you want to get mathematical about it, if it was just the integrator in the feedback, then the gain of the feedback path would be 1 over j omega rc. But the gain of the feedback path in Jason's circuit is 1 plus j omega rc. And when you plug that into the formula for the gain of an amplifier with negative feedback, which is our A over 1 plus AB, you end up with 1 over 2 plus 1 over j omega rc. And from that you can see that at high frequencies, when this 1 over j omega rc term disappears, the gain ends up being 1/2. And that's not that big of a deal for the gain of the overall circuit, because you can increase the gain of the back end by a factor of 2 to compensate for it. But that does make our common mode noise rejection a little bit worse. It's the job of the back end to actually do the rejection of the common mode noise, but it's not perfect, and some of the common mode noise is going to slip out to the output. The job of the front end, aside from being a buffer with high resistance inputs, is to have a higher gain for differential signals than for common mode signals. That way, when the signal actually gets to the back end, the signal-to-noise ratio is already better than it would be. The big problem with this DC offset tracking circuit is that it only reduces gain for differential signals and leaves common mode signals untouched, which means it's actually undoing some of the benefit that the front end is giving us. So for that reason, I would like to have a DC offset tracking circuit that does not reduce the gain. But the gain reduction also does something else interesting for us in terms of the frequency response. If you look at the plot, there's some corner frequency where the gain starts to level off, and that's the point where this 1 over j omega RC term becomes less important. So if you look at where it is with a gain of 1/2 and where it would be with a gain of 1, you can see that the corner frequency is actually lower now that we've reduced the gain. And this could be a good thing for us. The heartbeat signal is a pretty low frequency, or at least has some low frequency components, and we don't want that to get filtered out, so it's kind of nice to have a really low corner frequency. But the way you normally do that is by having a really large resistor and capacitor in the circuit. And the resistor and capacitor in this circuit are already 100 kiloohms and 1 microfarad, which are already pretty big. But here we can get the corner frequency even lower, basically for free, without having to change the resistor and capacitor at all. So not only do I want to not have any gain reduction from the DC offset tracking, but I also want to be able to do something similar and push the corner frequency down even lower. So here's a circuit I came up with that would do that. I use an inverting integrator instead of Jason's non-inverting integrator. And then instead of adding it to the negative signal, I subtract it from the negative signal and it has the same effect. But this time, because it doesn't have that 1+ term in it, it also doesn't reduce the gain. And I reduced the corner frequency by adding an attenuator in the feedback path. In case you don't know, an attenuator is basically the opposite of an amplifier. Signals that go in come out smaller. So now the gain of the feedback path is B over j omega RC, where B is the gain of the attenuator. And since the gain of the attenuator is going to be less than 1, that sort of has the same effect as making either the resistor or the capacitor larger. A good way to think about this is that the integrator will accumulate its input over time. So if there's a DC offset at the input to the integrator, then the output of the integrator will keep climbing and climbing and getting larger. Now normally that would just get subtracted from the input until it cancels out all the DC offset, but with the attenuator, it only subtracts off, let's say, half of the output of the integrator. Because the output of the integrator is going to keep on climbing, it'll eventually get to the same point, but it'll take about twice as long to get there. This means that any DC offset we have at the input is going to get tracked out at about half the speed as it otherwise would be. So if there's a DC offset at the input, it will still eventually get tracked out, but because it tracks more slowly, it won't be able to react fast enough to cancel out a low frequency signal coming into the input. And that's basically what it means to have a lower corner frequency on this filter. And after I come up with this, though, I noticed a problem with it. And that's that the integrator has a limited voltage range. There's some maximum voltage and minimum voltage that it can give at the output. And without the attenuator, that would be the maximum and minimum amount of DC offset that I could track out. But with the attenuator there, then I can only track out half that much. And that means that the range of DC offset that I can actually cancel out is only half what I otherwise would be able to do. In order to make sure I don't have too much DC offset at the input of the DC offset tracker, I would need to reduce the gain of the front end by a factor of 2. So then I'd be in the same situation that I was in with the last circuit, with the common mode gain reduced by a factor of 2, and then the common mode rejection was made worse. I could move the attenuator to the input of the integrator, and that would solve that problem, but the input to the integrator is differential, and I couldn't really think of an elegant way to move the attenuator over to the input. And that's why I came up with this. The DC offset tracking is not done in the differential part of the circuit anymore, which means I can put the attenuator at the input of the integrator. This also means that I can't have a gain of larger than 1 at the back end of the in-amp, so I need to compensate for that by putting another amplifier at the back end of everything else. And this is actually the same circuit as the first one I put together that had DC offset tracking, except it has this attenuator and this other amplifier on the back end. I originally wanted to put the DC offset tracking in the differential part of the circuit just so that I could have a gain of larger than 1 at the back end, because then the back end wouldn't be seeing any of the DC offset. This way I'm going to have to spend an extra op-amp making another amplifier on the end of everything else. But because this adder is built into the back end of the in-amp, I don't have to spend another op-amp as an adder in between the front end and back end of the in-amp. So in the end it has the same number of op-amps, it doesn't reduce the common mode rejection, and gives me a knob I can turn to adjust the corner frequency. So this is the circuit I'm going to go with, and I'll put this together and try it out in the next video.